couple more operations that we can do on our matrices. The first one that I want to talk about is something called the trace of a square matrix. Now remember, in the last lesson we talked about something called the main diagonal of a square matrix. And in order to calculate the trace of a square matrix, we're going to add all of the numbers that are on the main diagonal. And as long as we have a square matrix, the trace is always going to be defined. So for example, let's say we have this matrix. And we'd like to find the trace of this matrix. Well, we're going to identify the main diagonal of A. And we usually write TR. So TR means the trace, and the trace of A is defined to be the sum of the three entries on the main diagonal. Okay, so in our case we're going to get 4 minus 2 for a value of 2. The trace is always going to be a single numerical value. The trace will never be a matrix. Alright, take the time now to pause the video and try to calculate the trace of matrix B. Okay, remember what we do is we first take a look at the values on the main diagonal, and then we add them all together. So in this case, the trace of B is going to be -3 plus 5 plus 2 plus -4. Alright, this is equal to 0. Now this last operation that we're going to deal with in this video is kind of a strange one. It's called the transpose, and the idea is we take all of the rows of our matrix and then they become all of the columns of the new matrix. And what this equation is trying to tell us is that if we want the ij entry of the matrix called A transpose, we have to look at the ji entry of matrix A. And I should mention too, before we start working on any examples, that the notation for the transpose is this capital T. So let's go ahead and do a small 2x2 example together here. Now what I'm going to do is I'm going to circle each row of matrix A in a different color so that we can see where it goes in the matrix A transpose. Now this first row that we've circled in blue becomes our first column of matrix A transpose. So the numbers 2 and -1 now become column 1 of A transpose. And our second row, which is 0, 3, becomes our second column of A transpose. So it's not necessary in every example that you do to draw these circles around the rows and the columns, but for the sake of these next couple examples, just to help you visualize the process, I'm going to do that for you. So let's go ahead and work through a couple more examples just so you can get the hang of what transposing is going to look like. Let's work on the matrix B. If you prefer, you can also circle columns and turn those columns into rows. So in this case, our B transpose is going to look like this: -1, 3, and 0 as a single row. In other words, if we start with a column matrix, we end up with a row matrix, and vice versa. Okay, now for C transpose. I'm going to go ahead and I'm going to circle our columns. And each of these columns is going to become a row of our new C transpose. Let's go ahead and put our numbers in. Our first column becomes our first row. So in our blue row we have 2 and -1. In our red row we have 0 and 2. And in our green row we will have 1 and 4. Now I want you to go ahead and make an observation about the sizes. So take a look at C and tell me, what is the size of matrix C? Well, it has 2 rows, and 3 columns. Now go ahead and take a look at the size of C transpose. This one has 3 rows and 2 columns. What do you think? There's definitely a connection between these two numbers. When we take the transpose of a matrix, we end up switching these two numbers around. And the last idea I want to show you in this video is the idea of symmetry for matrices. We say that a matrix is symmetric if it satisfies the property that when we take the transpose of that matrix, it's equal to what we started with, the original matrix. And before I show you a quick example of a symmetric matrix, I want you to understand that A has to be a square matrix. Otherwise, it cannot be symmetric. Think about A if A was m by n. If we take the transpose of A, we've seen that these numbers switch order. So A transpose would be n by m. So there's no way that this equality could be satisfied because these numbers would be different. We would have different sized matrices. So in other words, A has to be an n by n matrix. Alright, so one last time here, let's take the transpose of matrix A. So I will make 2 circles, 1 for each row, and my first row, which is blue, becomes my first column, and my second row, which is red, becomes my second column of A transpose. So I read off row number 1 as 2, 0, so those values go into the first column. And 0 minus 1 goes into the second column of A transpose. And the important thing to notice here is even though we've switched the rows and the columns, A transpose is still equal to A. We still have all of the same numbers in the exact same spots as we did before. So A is a symmetric matrix. I'm going to leave you with just a couple questions to ponder about. The first one being the idea of these are really odd operations, and you might be wondering what the use of these really odd operations is. And that's a really good question. I can motivate a little bit about the transpose. We're actually going to have to use the transpose later on in the course, so we'll see the use of that later. As for the matrix trace, we're not really going to be able to do too much with that. If you take linear algebra 2, you're going to see a use for that perhaps when talking about eigenvalues. Other uses that I can recall from my math career are we can use trace to classify Mobius transformations, so that's something that you can do in complex analysis. As well as, I know I worked a little bit in character theory, and that was in a field of mathematics called group theory, in which the trace can be used to talk about characters of a representation. Essentially, the uses of the trace are in a bit higher mathematics than where we're at right now. And the other question I'm going to leave with you is, are there any nice properties of symmetric matrices? And once again, the answer is yes. There's some really great properties, and I encourage you to go take a look and try to find some of those properties on your own. Alright, my little epsilons, stay positive.